which is 1. So let's use that one. Let's just see where it takes us. So I get limit x approaches 1 of f of x. That's my top left corner here, f of x. What is f of x? Well, it's this. So I'm going to write that whole thing down as a fraction. 2x plus 1 over x plus 2 minus what we get when we plug 1 in. Well, we already know what happens when we plug in 1, right? We should get 1 because that point lives on that graph. But you could verify it. Just plug it in. Plug in 1, you get 3 over 3. So you get 1. So it's all of that minus 1. All of this over x minus 1. Okay, at this point, if you try to let x be 1, what you're going to get is 0 over 0. So again, we're going to need some sort of algebra to try and work this out. So here's the algebra that I'm going to employ here. I'm going to, because I have a fraction up here, and then a bigger fraction, so this complex fraction, I'm going to look in the numerator, I'm going to get a common denominator. So what I mean by that is I'm going to try and get this 1 to be rewritten as 1 over 1, and then I'm trying to get the same denominators on the bottom here. So what I need to do is make an x plus 2 appear down here. The only way to make an x plus 2 appear down here is to multiply the bottom and the top by x plus 2. That's still a 1, but I've rewritten it so I can combine these two fractions together. So what I have now, limit x approaches 1, is I'm going to have this top. I'm going to subtract this, so be careful that negative sign will carry through. So I'll have 2x plus 1. I subtract x, I subtract 2. All of that over the common denominator, which was x plus 2. All of that over the original denominator there, x minus 1. And if things work out nicely here, we should get something to cancel. Let's see. We have 2x take away x, that's x. We have 1 take away 2. It's going to be negative 1. So we have x minus 1 over the common denominator, x plus 2, over the original denominator, x minus 1. And now I have a fraction over a fraction because I can look at that x minus 1 as being over 1. And what I can do is rewrite a fraction over a fraction, or a fraction divided by a fraction, as multiplication of the reciprocal. So I'm just going to take the fraction on the bottom and flip it and bring it up as a multiplication. So this got flipped and came up. And now you can see quite a nice thing happens. Those cancel. So I'm left with limit x approaches 1 of 1 over x plus 2. And now let x go to 1, you get 1 over 3. So this limit is 1 over 3, which means the slope of my tangent line is 1 over 3. So now I can rewrite or use that formula, y minus y1 equals m times x minus x1. So y minus y1 was 1, my slope was 1/3, and then x minus my x1, which was 1. Distribute. This is not absolutely necessary, but I encourage you to just take this all the way and try and solve it for y. I'm going to add 1 to both sides. 1/3, negative 1/3 plus 1 is 2/3. There we go. That is the equation of your tangent line. I'm going to do one more and I'm going to take a little break. By the way, if you're wondering why I'm taking breaks and stuff, it's because this video originally, when I made it in class, the audio didn't pick up, so I had to redo it at home. So that's what I'm doing right now. Okay, so we want to find the slope of the tangent line to this graph at the point, or at, I should say, x equals a. So this time they don't give us a point, right? They don't say like 2, 5, or something like that. They don't give us anything like that. They just say, hey, look, at a, what's the slope of the line here? So they're not asking for the equation. They want find slope. So find slope tangent line. All right, well, we have one of two definitions that we can use. I'm going to go ahead and use this definition. Slope tangent line equals limit x approaches a, fx minus fa over x minus a. So this should give us the slope of the tangent line at a. Does that make sense? And look, We want to know what's happening when x is a. Well, that's what this formula tells us. It gives us a general answer for any value of a. So if a was 2, we just replace that with 2, but we're not going to. We're just going to leave it. So let's just try and figure out what this turns out to be here. We have limit x approaches a of f of x. Now, f of x is just this. So f of x is 1 over square root of x minus f of a. Well, what happens when you plug a in right there for x? You just get 1 over square root of a all over x minus a. Ooh, this does not look good. If we right now let x become a, right, so let that x and that x become a, we're going to get basically 0 over 0. So nothing works there. At that point, that didn't help. So we have a fraction on top over this bigger fraction. So like I just said, we're going to try and get a common denominator. So to get a common denominator, I'm going to need a square root of x here and a square root of x here, and then a square root of a here and a square root of a here. That way they both have the exact same denominators. So let's go ahead and do that. So we're multiplying by 1, right? This is a 1 right here. This is a 1 right here. Root a times 1 gives me root a. I need to rewrite this limit. Give myself a little more room. Okay, root a over root, I'm just going to say ax. I can put them together. And then, let's see, 1 times root x is root x over root ax again. Then all of that divided by my common denominator. Now that they have the same denominator, or sorry, I said common denominator, all divided by the original denominator there, x minus a. But since these two have a common denominator now, I can put them together, which just means I take this, subtract this. And let's see if that gets us anywhere. Limit x approaches a of root a minus root x over root ax all over x minus a. Unfortunately, nothing looks like it's going to cancel here, right? We were hoping that maybe this would cancel out with something up here, but it doesn't. So now here I come again with my tricky algebra inside of calculus here. I'm going to multiply by 1 here, very special 1. I'm going to choose to bring in the conjugate of the numerator up there. Now, conjugate, the reason I'm thinking conjugate is because conjugate, when you do it, it gets rid of roots. So whatever I do on top, I have to do on the bottom. So notice I've inserted a 1 here. That's a 1, right? So I haven't changed the problem. And I'm going to multiply this through, so I'm going to do like a foiling up here. And let's go ahead and see where that gets us. So limit x approaches a. Let's see that first multiplication. The roots cancel out, you just get a. We know that the middle two are going to cancel each other out, so I don't have to worry about that. My last multiplication, negative root x times positive root x. Negative times positive is negative, and the roots will kill each other off. Now, below that, I had that root ax there, and I had to multiply that times that conjugate, which I'm not going to do. I'm just going to leave it written like this. I'm not going to distribute that. All over the bottom, which is x minus a. And look at this. We have a minus x up here and x minus a down here. And those are almost the same. They're just off by a sign. So remember, the bottom here is a fraction. So if we look at this division bar, we have a fraction on top divided by a fraction on the bottom. And so we can flip it and let it become multiplication of the reciprocal. So let me do that. Limit x minus a, or x approaches a, of a minus x over that root ax times root a plus root x. Now I'm flipping the denominator and bringing it up here. It's 1 over. And then instead of writing x minus a, I'm going to factor out a negative 1, or negative, and make it instead a minus x. And now, hopefully you see that these two are the same and they cancel. But we still have that negative there, so we have to keep count of that. All right, so here's where I am. I have limit x approaches a. That negative that was down here, I'm just going to pop it to the top, make it a -1 over root ax, and then in that parentheses, root a plus root x. And now I'm ready to let all my x's become a's. Nothing changes up here. Notice the limit's gone now. I have root a times a, and then I have square root a plus this is now square root a. So I have -1 over, this right here is a squared, but then square root, so you should just get a. And then times root a plus root a is 2 root a, so 2 root a. And this, my friends, is the slope of the tangent line. Now you could write that a different way, because remember, you could write that denominator like this, or you could write that as square root of a is the same as a to the 1/2. So you could write that as a to the 3/2 by using the properties of exponents, that you would add the exponents. 1 plus 1/2 is 3/2. So that denominator could be this, right? That could be how you rewrite that. So that's it. That is the slope of the tangent line at A. So now if someone says, hey, what's the slope of the tangent line of this graph at 4? You would just come over here and you just plug 4 in right here. If they said, oh, what's the slope of the tangent line here at 9? You just plug 9 in. So for pretty much any positive value of A, we could figure this out. All right. Let's see if there's anything else here. Let me take a quick break. Okay, back to business here. I want to take this result here and just show you a couple of ways we could use this. Remembering that the whole idea here was that if we have a graph here and we want to find the tangent line at any value of x, we can do it in general and get a general answer. And then if someone says, you know, find the equation of the tangent line to y equals 1 over the square root of x at, let's say, 4, 1/2. So that's a point on the graph. Then using what we just figured out, we know that the slope of the tangent line at any point, x equals a, is -1 over 2a root a. So if here a is 4, we plug in 4 here, you get -1 over, let's see, 2 times 4 is 8 times the square root of 4, which is 2, so we get -1/16. So we know we have a negative slope there. So the equation of tangent line would be y minus y1, which is 1/2, equals the slope, -1/16, x minus x1, x minus 4. And then we could simplify it. We could try and get y by itself, but that's the equation. So, and I could do that for any point. So finding a general solution is actually pretty valuable, because it speeds up the process if you're trying to find equations of several tangent lines. All right, let's take a look at another example. How about using now this whole concept of the general derivative? So if we have this, and you're asked to find this. So this is f prime of a, which means the slope of the tangent line at a, okay, at x equals a. So we can use two definitions to do this. I'm going to use the first definition, or the one that we've been using, limit, whoa, lost my drawing there. X approaches a, f of x minus f of a.